Okay. Looks like maybe I mislabeled this. Did I really type 2311? Oh, shit, I did. All right, that's okay. Bit of a rough morning. But I do see that it's in the right place. The right people are getting here, so that's good. All right. Thank you for your patience this morning, guys. I really appreciate that. This is just one of those days when I needed a couple extra minutes to get going. I know we all have those days, and I appreciate you understanding when I have them. We get the dot cam set up, and we can get rolling. All right. So last time we finished talking about trig integrals. Today I'd like to do a few things. We can look at any homework problems that you have questions about from the trig integral homework. And then I want to spend the latter part of the class preparing you for trig sub, which is the next section. It's a little bit of a tough section. But first, homework questions. Okay, so this is the plan for the day. Hopefully my camera will focus. Oh, and let's get this going. There we go. All right. So I will take any questions you guys have from the 7.2 homework beat. Sure, of course. What else would we like to see besides 16? Yeah, 16 is pretty quick. It's not a hard problem. Just requires a little trick. What else would we like to see? What else has been difficult or are we uncertain about? If you haven't had the time to go through the homework and you don't have a list of questions that have stumped you or been difficult for you, I invite you to take a look right now and see if there are any that look intimidating so we can make good use of this time. The first problem that was requested here by Colin, the integral of 1 over cos x minus 1 is not terribly hard, but it does require a little trick. So imagine you're back in trigonometry and I gave you this thing, 1 over cos x minus 1, and I asked you to write it in terms of secants and tangents. So to break everything down in terms of sine and cosine, and then give me a nice simple product involving just powers of secant and powers of tangent. What sort of things come to mind? This is kind of a nice intro to trig sub on its own. I'd like to see if anybody has thoughts on this before I jump in and just show you. That would be nice, but I don't have a cos squared yet. Subbing for cos x minus 1 might be interesting, but it's not going to work out nicely. So yeah, let's deal with some algebra issues first. So 1 over cos x minus 1. This is not the same as 1 over cos x minus 1 over 1. This sort of business doesn't work. Fractions, you can split them up nicely across their top, but you cannot split them up across their bottom. It's true that 1 over cos x is secant x, and the fact that we've got cosines downstairs suggests that something like secants can arise at some point. But this game would not work. I cannot write this as secant x minus 1. It's true that this is equal to secant x minus 1, but the thing I'm starting with is not equal to this, because fractions don't play nice like that. So when you're tempted to do something like this, you should ask yourself, are there other similar situations I've seen in algebra or trig classes where I've been tempted to try something along these lines? And I'll remind you that cosine, remember all of the fundamental trig functions, sine, cosine, tangent, by use of the Pythagorean identity can kind of be thought of as square roots of differences, right? Like cos x is the square root of 1 minus sine squared x. So when you see something like that, think back to your algebra classes, you had something like this. If you wanted to take a limit or do anything kind of challenging with this, usually the first step would be multiplying by the conjugate, right? You guys remember this sort of trick? Well, cos x is a square root. It's the square root of 1 minus sine squared. So if we try multiplying by the conjugate, so this is not going to work. But what will work is multiplying top and bottom by the kind of conjugate of that expression. Now remember, the fractions are grouping symbols, so we have to think of it like that. So you'll have to like FOIL distribute. The numerator will just be 1 times cos x plus 1. That's cos x plus 1. The denominator, if we distribute this times this, that's cos squared x. And then I'll have minus cos x from my inners, plus cos x from my outers. Those will cancel, they'll go away. And then I'll just have minus 1 from my lasts. And you might be saying, okay, John, well, how the hell is that better than what we started with? Well, you know that sine squared x plus cos squared x is equal to 1. And if I subtract sine squared from both sides, that tells me that cos squared x is equal to 1 minus sine squared x. And then if I subtract 1 from both sides, that tells me that cos squared x minus 1 is equal to the negative of sine squared x. So this piece down here, cos squared x minus 1, I could replace by negative sine squared x. And now we're moving in a good direction, because remember, the challenge here is that I had this subtraction downstairs, and I couldn't split up over that. So my next step is going to look like this. I'll have the numerator is cos x plus 1. The denominator is negative sine squared x. And then I'll pop that negative out and split up the fraction over its numerator, because that is allowed. So that's cos x over sine squared x plus 1 over sine squared x. And the negative from the negative sine squared is now out front. Oh, I wish I had more coffee. Okay. So remember my suggestion at the start was to try and rewrite this as powers of secant times powers of tangent or something like that. Now we're in good shape to do that. 1 over sine squared, well, 1 over sine x, that's cosecant x. What about cos over sine squared? I can rearrange a little bit and write this as negative integral cos x over sine x times 1 over sine x dx minus the integral of 1 over sine squared x dx. Yeah, so that very first piece here, this is cotangent, this is cosecant, and this is cosecant squared. So you have to be very fluid with your trig knowledge. That stuff needs to be right there on top of your brain. This is negative integral cotangent cosecant minus the integral of cosecant on its own. Sorry, yeah, thank you, cosecant squared. Yes, good. All right, let's do this one first. Who differentiates to, or either one, I guess, who differentiates to cosecant cotangent? Who differentiates to cosecant squared? Good, yeah, this first guy, remember the derivative of secant is secant tangent, so the derivative of cosecant is negative cosecant cotangent, which means the integral of cosecant cotangent is negative cosecant, and similarly, the integral of cosecant squared is negative cotangent. So remember, the cofunctions follow the same derivative patterns, they just have negatives out front. Secant differentiates to secant tangent, so cosecant differentiates to negative cosecant cotangent. Sorry, there should be a negative in here. There we go. And then these two negatives and these two negatives make positives. So this is going to be this good old-fashioned cosecant x plus cotangent x plus c. And the two things we needed to get here were the multiply by the conjugate trick and then the first Pythagorean identity rearranged. Questions on this guy?
I had one question.
Yeah.
Just like a simple thing. Right where your fingers are right there, is that symbol a minus or a plus or something?
This is a minus.
Keep going. To the right, that thing right there.
That's a plus.
Oh, okay. I was confused by that.
Yeah, sorry. That's a plus. So,
Thank you.
yeah, we had the negative from the negative sine squared. I popped that all the way up front. And then this is coming from splitting this fraction up over its numerator. So it's cosine over sine squared plus 1 over sine squared. Any other questions on this one? Okay, if not, Amanda wanted to see number 4, so we'll go to that next. Oh hell. So we actually did this one, I think we've done this one a couple times now. We did this one in class on Monday. Sine squared times cos to the 4th. So I don't want to burn too much time on this, but we can take a quick look because I know that these are somewhat tricky. Here, both of the powers are even, right? The power of sine is even and the power of cosine is even. That means you have to use half angle identities. Right? If you're doing a sine cosine integral and both of the powers are even, then the only thing to do is to bash the thing to death with half angle identities until it turns into something you can handle. Remember, if one of the powers is odd, then you're going to try u sub. But if both powers are even, then this is the only tool we have. The half angle identities that you use here are cos squared theta equals 1/2 times 1 plus cos 2 theta, and sine squared theta equals 1/2 times 1 minus cos 2 theta. Now, I really do think we did this exact problem, not yesterday, but Wednesday. So I'll show you the first few steps. But I think our time would be best spent elsewhere. Cos to the 4 is cos squared squared. So I start by, oh shit, this is a cosine 2t. So I start by using the half angle identity for sine to rewrite sine squared t as 1/2 1 minus cos 2t. And the cos to the 4 I write as cos squared squared. So I get integral 0 to pi 1/2 1 minus cos 2t times 1/2 1 plus cos 2t squared. Here I need to square the 1/2 and the 1 plus cos 2t. Here I have a regular 1/2. So that's going to be 1/4 times 1/2 is a 1/8 coming out front. Then integral 0 to pi 1 minus cos 2t times 1 plus cos 2t squared. And we distribute everything. Following my order of operations, first I have to square out this guy, which is 1 plus 2 cos 2t plus cos squared 2t. And then I have to distribute this term across this term. So I'll distribute the 1 and then the minus cos 2t. So that's 1 plus 2 cos 2t plus cos squared 2t minus cos 2t minus 2 cos squared 2t minus cos cubed 2t dt. And then we combine our like terms. So we got 1/8 integral 0 to pi 1, and then plus 2 cos 2t minus cos 2t is plus cos 2t, plus cos squared minus 2 cos squared is minus cos squared 2t. And then I've got minus cos cubed 2t dt. Through this process, I've introduced an odd power. Remember, odd powers of sine and cosine, they get a different treatment. Even powers, we just beat them to death with half-angle identities. But odd powers, we use u sub on these. So I'm going to break this guy and handle him separately. I'll break this into his own integral and treat him with different means. This fellow needs to be broken down also. He's still an even power. So here, I'll use the identity, the modified half-angle identity. So if cos squared theta is 1/2 times 1 plus cos 2 theta, then cos squared of 2t is 1/2 times 1 plus cos of 4t. Right, just replacing theta by 2t in this expression. This is our modified half-angle identity. And we've had to use this a few times. So I'll go 1/8 integral 0 to pi 1 plus cos 2t minus 1/2 times 1 plus cos 4t, and then minus 1/8 integral 0 to pi cos cubed 2t dt. Oh, I left off my paren dt here. So I'll distribute this 1/2 over this term. And then here I need to do something else. We get 1 plus cos 2t minus 1/2 minus 1/2 cos 4t minus 1/8 integral 0 to pi. The way we handle these odd powers, cos cubed, for example here, I grab one copy of the odd powered function, set it aside. So I'm going to grab one copy of cosine and set it aside, and then I'll rewrite the remaining 2 cosines as sine. So this is, I'll do it in 2 steps. Cos squared 2t times cos 2t dt. And then here I'm going to make the substitution. Oh, I'll do it on another page. So I can combine my like terms here. One and minus 1/2, those are like terms. That'll give me a positive 1/2 plus cos 2t minus 1/2 cos 4t dt. And then this guy, I'm going to rewrite the cos squared. This is minus 1/8 integral 0 to pi 1 minus sine squared 2t times cos 2t dt. And I want to make the substitution here, z equals sine of 2t. So dz would be 2 cos 2t dt. We also have to change our bounds. When t is equal to 0, z is equal to the sine of 2 times 0, which is also 0. And when t is equal to pi, z is equal to the sine of 2 pi, which is also 0. So you get minus 1/8 integral 0 to 0, 1 minus z squared times 1/2 dz. Which is a little bit interesting. Integral 0 to 0, those don't show up too often. If you're integrating from 0 to 0, or from 1 to 1, or from pi to pi, the result is always 0, because the width is 0. There's no room for there to be any area there. So this integral is 0 because the integral from a to a of anything is always 0. This guy is ready for his antiderivative step. One half integrates to 1/2 t. Cos 2t is going to integrate to sine 2t over 2. And minus 1/2 cos 4t is going to integrate to minus sine 4t over 8. The cos 4t integrates to sine 4t over 4, and the 1/2 makes the denominator there an 8. And again, the contribution from this piece is nothing. If I plug in my lower bound of 0, the sine of 4 times 0 is the sine of 0, that's 0. Sine of 2 times 0 is the sine of 0, that's 0. And 1/2 times 0 is 0. So the lower bound here doesn't contribute anything because all three of these terms are 0 at the lower bound. If I plug in the upper bound, the sine of 4 pi is 0. The sine of 2 pi is 0. So the only contribution comes from this term at this bound. We get 1/8 times 1/2 pi, or pi over 16. So if you want to see that done a little bit more slowly, go back and watch the video from last time. We did go through it with a little bit more care, but this is the procedure. Are there any questions about any of these steps? Where did this come from? Why did we do that? How did we know to do that? Yeah, so your constants may be a little bit different than my constants. I didn't include any constant in front of my integral because, like you say, Alex, there are randomly generated Levissine constants in front there. I don't recommend just writing the answers that I give you here into Levissine. You're going to shortchange yourself. You need to go through this process on your own and make sure you understand the steps. So the purpose of us doing these in class is not so you can just input the answers. The purpose is so that you have something to look back and guide yourself if you get lost while you're working the problem on your own. But what you said is correct, Alex. Margaret would like to look at number 15. Any other questions about number 4 before we move away from it? Okay. I'm going to do the same thing here on 15 and ignore the Levissine constant out front. But we want to integrate from pi over 6 to pi over 2, the square of the cotangent function. So like we said before, the cofunctions follow the same patterns as the regular trig functions, just with negatives. How do you integrate tangent squared? Yeah, that's the game, right? There's a Pythagorean identity that relates tangent to secant. There's also a Pythagorean identity that relates cotangent to cosecant. So these are your three Pythagorean identities, and the bottom one implies that cotangent squared is cosecant squared minus 1. So I rewrite this guy because I have no idea who differentiates to cotangent squared, but I do know who differentiates to cosecant squared. So I rewrite this guy as the integral pi over 6 to pi over 2 cosecant squared theta, or sorry, cosecant squared x minus 1 dx. And now this is actually easy, right? Who differentiates to cosecant squared? We did this a minute ago. The derivative of tangent is secant squared. So the derivative of cotangent is negative cosecant squared. So yeah, so negative cotangent would integrate to cosecant squared. So my antiderivative step is like this. And now I just have to evaluate between bounds. The cotangent of pi over 2, what is that? We need to know our unit circle, right? This is a necessary thing for this class. Tangent of pi over 2 does not exist, but cotangent of pi over 2 is perfectly happy. Good, it's 0, right? Cotangent is cosine over sine. The cosine of pi over 2 is 0, the sine of pi over 2 is 1. So the cotangent of pi over 2 is 0 over 1, which is 0. So from my upper bound, I'll have this. And from my lower bound, the cotangent of pi over 6, anybody? This one's a little trickier. That's the cosine of pi over 6 divided by the sine of pi over 6. Good, square root 3. Yeah, you could write it as root 3 over 2 divided by 1/2, but then if you flip and multiply the 1/2, you just find that it's root 3. So negative cotangent of pi over 6 is negative square root of 3. And then I have to also have my minus pi over 6 here. So that's that. And there's not much that can be done to clean this up besides distributing the negatives. So I'll have root 3 plus pi over 6 minus pi over 2. You could combine the pi over 6 and pi over 2 if you want. Pi over 2 is 3 pi over 6, so that is 1 pi over 6 minus 3 pi over 6 is minus 2 pi over 6, or minus pi over 3. So this is a fun problem. It's mostly just about knowing your unit circle, right? I think the steps there that would trip up most people are down here. But also you need to know how to integrate tan squared in order to really think about how to integrate cotangent squared. So I would say that this is similar to which we should also kind of remember. I don't expect anybody to have the answer memorized, but the procedure you should be comfortable with. All right, rewriting tan squared as secant squared minus 1. Okay. Is there anything else from the homework that you guys would like to take a look at? 17, sure. Yeah, I see a few ways we could attack this. That's a definite integral, no, indefinite, okay. So in number 17, we want to integrate x times sine squared of x squared dx. Has anybody attempted this? Has anybody tried anything yet? IVP is definitely an option, but I think substitution is a better option, yeah. If I wanted to run IVP and followed LIPET, then I would pick this to be U and this to be dV. But the step passing from dV to V would be hard. I don't know how to integrate the sine squared of x squared on its own. So actually having that x out front is really nice. In other words, we're going to think of this as sine x squared times x dx, and then we're going to substitute z equals x squared. dz is then 2x dx. It's an indefinite integral, no bounds, so I don't have to change any bounds. This x dx is 1/2 of dz, because dz is 2x dx. So I'll get a 1/2 out front, and then integral sine squared z dz. So a little bit of u sub or z sub to get started. And then from here, the integral of sine squared, well, that's a sine cosine integral, and the power is even, right? There are no odd powers here. So I'll use half angle identities. Sine squared z is 1 minus cos 2z. And then it's a kind of micro u sub, right? So the 1/2 comes along for the ride. 1 dz integrates to z minus cos 2z integrates to sine 2z over 2. And since this is an indefinite integral, we have to go back to the original variable at the end. I'll go ahead and distribute the 1/2 also. So we'll get 1/2 x squared, z is x squared, minus the sine of 2x squared over 4. Okay. Let's see, is there anything else in here? Grind on. I got a 1/2, did I? So this turns into this because z is x squared, and this 1/2 and this 1/2 make a 4 down here. Oh, yeah, you're right. You're right. I did lose a 1/2. I'm sorry. This sine squared z is 1/2 times 1 minus cos 2z. So this should be a 1/2 squared. So this will be a 1/4. Yeah, you're absolutely correct. I did lose a 1/2. And this will be a 1/8. Yeah, the 1/2 from my trig identity. So here when I replace sine squared z by 1/2 1 minus cos 2z, there should be another 1/2 coming out. So this is really a 1/4. Yeah, thank you, Griffin. There's Zach, good catch. Yeah, it's not too bad. And in fact, you'll find none of these are really too bad. All of these trig integrals are fairly straightforward once you practice with them a little bit. Number 20, you'll use the double angle identity for sine. You'll write that as 2 sine x cos x. And then you'll have cos cubed times sine. This guy is again not bad. This one is fun. It looks like it's going to be a long problem, but it's not. It's just showing you 3 different ways to do the same integral. This fellow we just did, this fellow we just did, this one we just did. This guy you'll rewrite in terms of secant and tangent, see what you get. Yeah, none of these are too horrible. All of the integrals here, 10 through 13, those are 9 through 13, 8 through 13, 7 through 13. Those are classic secant tangent integrals, which you can resolve with u sub with, I think, one exception. Let's see, are any of these? It is. It's just about knowing your trig. And the reason we do this section right now is because the next section requires you to know your trig. And rather than that being the point, it's kind of a background thing. So you have to be a master of trig to have a chance at trig sub. And that's what I want to introduce in the last few minutes of class here today. So we're going to do a little intro to section 7.3, which is on trig sub. Each of the Pythagorean identities explains how to interpret a basic trig function as a square root. If I subtract sine squared from both sides and take square roots, I'll discover that cos theta is the square root of 1 minus sine squared theta. Here I could say that secant theta is the square root of 1 plus tangent squared theta. Or I could say that the second Pythagorean identity implies that tangent of theta is the square root of secant squared theta minus 1. So earlier when I said that multiply by the conjugate thing makes sense because I can think of cos x as a square root, I wasn't playing around. I meant that very literally. So if I encounter an integral containing an expression like the square root of 1 minus x squared, or the square root of 1 plus x squared, or the square root of x squared minus 1, then I want to sub x equals sine theta in that first guy, because the square root of 1 minus sine squared sine squared theta, that's the square root of cos squared theta, which is just cos theta. If I encounter a square root of 1 plus x squared, I want to let x be tangent theta, because then the square root of 1 plus x squared becomes the square root of 1 plus tan squared theta, which is the square root of secant squared theta, which is secant theta. And if I had an integral with the square root of x squared minus 1, then I would want to let x be secant theta, because the square root of x squared minus 1 would then be the square root of secant squared theta minus 1, which would be the square root of tan squared theta, which would be tangent theta. So these are the sort of substitutions we're going to be making in section 7.3. Your integrals aren't going to start out with any trig functions. They'll start out with stuff that looks like this. But when you make a substitution like this, you'll be introducing trig functions. These are substitutions, so when you make these indefinite integrals, you will have to change your bounds, and that's going to require you knowing your unit circle well. Not at the end of the problem now, but in the middle of the problem. So you'll be stumped right away if you don't know your unit circle, so it is critical that you know that thing. Another interesting thing here these are kind of backwards substitutions. Because my old variable is being made equal to a function of my new variable. So the old variable here is x, the new variable here is theta. Normally when we make a substitution, I let my new variable be some combination of the old variables, like I let u equal x squared, or I let z equal x minus 1. Here I'm letting x, my old variable, be equal to sine theta, so my new variable is trapped inside here. That means the differential work goes a little bit differently. That's the main upshot there. So I'd like to show you how one of these goes. This changes how we handle the differential. So one of my favorite things to do when introducing this content is to go back and prove some stuff that, in theory, you already know. And that way, in the event that you don't remember it, we will have also jogged your memory. I think most of us remember this integral. We know that this should come out to the inverse tangent of x. However, if you forgot that, because of this 1 plus x squared here, that's kind of a hint that you could try some trig sub. I could let x be the tangent of theta. And then I differentiate on both sides to get my differential. Dx would be secant squared theta d theta. And so these backward substitutions are actually easier in a sense, because rather than having to find something floating around here to soak up your differential, you just get dx equals some mess. You can just plug this in for dx. It's tragic that people so often forget the differential when doing trig sub, because it's easier than it is in doing u sub or z sub. If I plug those in, that's literally all I'm doing. I'm just plugging in tangent theta for x squared and secant squared theta d theta for dx. I get integral 1 over tan theta squared times secant squared theta d theta, which is integral secant squared theta over 1 plus tangent squared theta d theta. And downstairs, 1 plus tangent squared, that is secant squared. So this is integral secant squared theta over secant squared theta d theta, or just the integral of 1 d theta. Integral of 1 d theta, that's theta plus c. I thought you said this was going to come out to inverse tangent. Well, it does. Now you go back to your substitution here, and you say, okay, if x is the tangent of theta, then the inverse tangent of x is theta. So this whole apparatus is the inverse tangent of x plus c. And that's trig sub. Gets a little trickier in definite integrals. And if I'm honest, most indefinite integrals are a little bit trickier than this also. It's kind of wild, but really it's the same thing as u sub, just being done backwards. And with trig functions. There's another simple, straightforward example like this that I'd like to show you. And then if there's time, maybe I'll show you one slightly rowdier example. Well, I trust everybody remembers the integral of 1 over 1 plus x squared. So we really didn't need to go through that for you to know that that's arctan. I suspect that fewer people would remember what this is right away. Good, yeah, it's arcsine, right? The derivative of the inverse sine function is 1 over the square root of 1 minus x squared. But what if I forgot that? Well, if you look back on this page, we said when you see a square root of 1 minus x squared, you might try letting x be sine theta, because that will clean up the square root. So the whole game here, guys, is that these square roots suck, right? Square roots of things like this is not the same as just 1 minus x. You can't distribute the square root. That never works. So when you encounter square roots like this in your integrals, usually the challenge is to get rid of the addition or subtraction underneath the square root. And that's the magic of these trig identities. They do exactly that. So again, square roots do not distribute over addition or subtraction. This thing is not 1 minus x. This thing is not 1 plus x. And this thing is not x minus 1. That shit never works. But if you can get rid of the addition or subtraction underneath the square root, then you're golden. So in this guy, I want to let x be sine theta. And again, the differential work here is easy. Dx is going to be cos theta d theta. So everywhere there's an x, I write sine theta, and in place of dx, I write cos theta d theta. And I'll get 1 over the square root of 1 minus sine squared theta. If x is sine theta, then x squared is sine squared theta times cos theta d theta. And 1 minus sine squared, according to our first Pythagorean identity, is cos squared. So you get 1 over the square root of cos squared times cos theta d theta. That is just cos theta over cos theta. So just like the previous example, this becomes the integral of 1 d theta. Things will not usually simplify this nicely. Usually at this step, you'll have a more complicated trig integral to do. I'm just using these two as very, very gentle introductory examples. Integral d theta is still theta plus a constant. And again, we can come back to our substitution here and say, okay, well, what is theta? If x is sine theta, then the sine inverse of x has to be theta. So this is, as was observed in chat, inverse sine. All right. You can imagine I could cook up an example like this for each of the 6 trig functions, right? One of these comes out to arcsine, one arc cosine, one arctan, and so on. The real big news here is that this is going to let us start to integrate stuff that we could never integrate before. So the first kind of full-throated example is finding the area of a circle. And I'm going to go back through this on Monday. Here we'll get a picture for the sort of things we can integrate now that we couldn't integrate before. Find the area of the unit circle. We know that the formula for the area of a circle is pi times the radius squared, so I'm expecting the area here to come out to pi. The equation for the unit circle is y squared plus x squared equals 1, which can be solved as y equals the square root of 1 minus x squared. Really, there's a plus or minus in front there. So this is the equation of the upper semicircle. Right, the second equation there is the equation of the upper semicircle. So if I wanted to find the area of the circle, I could integrate the square root of 1 minus x squared from 0 to 1. Right, this is the point 1 comma 0. Of course, the origin is 0 comma 0. And if I want to find the area underneath this curve from 0 to 1, I just integrate that. So the area of the whole circle is 4 times the integral from 0 to 1, the square root of 1 minus x squared dx. And previously, we had no hope at integrating this. We'll be clear about that. U sub doesn't work. IBP doesn't work. But this looks a lot like something from that table we just looked at. So here I'm going to let x be sine theta. Dx is then going to be cos theta d theta. And now this is a definite integral, so you're going to have to change your bounds. And I think changing the bounds, a lot of people have trouble with here, because if I'm honest, trig at Santa Fe sucks. I'm working to try and change that, but if you took trig here, then you probably didn't get a great treatment of it, sadly, unless you took it with like Aaron or Dr. P or something. So to change the bounds, you do the same thing you always do. You plug your old bounds into the substitution. So when x is equal to 0, this equation becomes 0 equals sine theta. So you have to solve equations like this to change your bounds. So theta would be the inverse sine of 0. And unless you remember your unit circle well, this is going to be hard. What is the inverse sine of 0? No, it does exist, and it's just one number. So let's do a little quick review of inverse trig.
That is 0.
A is the sine inverse of B means, or is defined by the rule, sine of A equals B, and A is between negative pi over 2 and pi over 2. So these definitions, including the domain restriction stuff, you gotta remember that. If you don't remember that, if you did not get a good treatment of inverse trig back in your trig class, it's time to drum it up. And that's why in the review module in Canvas, I have lots of links to inverse trig things. You're gonna need those. So if this is rusty, if you don't remember that the answer here is the one number 0, and you can't explain exactly why, you probably want to go look in those modules and review some of the inverse trig stuff there. Let's try the upper bound. When x is equal to 1, we have the equation 1 equals sine theta, which means theta is going to be the inverse sine of 1. So theta equals inverse sine of 1 means that the sine of theta equals 1 and theta is between negative pi over 2. Ooh, this should be inclusive, and pi over 2. Good, pi over 2. The inverse sine of 1 is the unique number pi over 2. So there's your substitution. Now we can go ahead and plug it in. So a is equal to 4 integral, I'm just going to rewrite it here, square root 1 minus x squared dx, which is the integral 4 times the integral from 0 to pi over 2 of the square root of 1 minus sine squared theta times the differential, which is cos theta d theta. And the magic here is that good shit's going to happen underneath the square root. 1 minus sine squared theta is cos squared theta. So this is 4 integral 0 to pi over 2 square root of cos squared theta times cos theta d theta, which is the integral from 0 to pi over 2. The square root of cos squared is cos. Cos times cos is cos squared. And then from here, it's turned into a problem from section 7.2. Use your half angle identity. And then you take your antiderivative. Oh, shit. I lost the 4. God damn it. Thank you. Thank you, thank you. So that's 2, 4 over 2 is 2 times, and I need to evaluate between bounds. At my upper bound, I'll have pi over 2 plus the sine of 2 times pi over 2 divided by 2. And then at the lower bound, both of those guys are 0. I'll write it. The sine of 2 times pi over 2 is the sine of pi. That's also 0. So the only thing that survives there is the pi over 2. And so we get pi, as we expected to do. Because the area of any circle is pi times the radius squared. And this is the unit circle, whose radius is 1. So I'm not going to do any more examples today. I'm going to stop here. I want to talk about some common mistakes, though. This is just driving me crazy. Why does that keep making noise? Oh. Common mistakes here are not being familiar enough with the unit circle, simplifying this as 1 minus x before doing anything else. That, of course, is not at all kosher. And then another common mistake is writing down something like x equals sine of x. Can't do that. Got to use a new variable here. It doesn't have to be theta. If you don't want it to be theta, you can use w or t or whatever you want. But this and this have to be a different variable. And then the last common mistake, for whatever reason, is just ignoring the differential altogether, right? If you don't write this dx here, you might forget to write the cos theta d theta here. That's one of the reasons why I harp on you guys and so much to write the differential, the dx. It really does have a meaning, and if you forget what that meaning is, or if you don't write it, you may omit very important things in these problems. So this is the sort of stuff we're going to be doing next week. Monday of next week, we're going to cover trig sub. It's going to go fairly quickly, but then the problems, I suspect, will take you a little while. There's not a whole lot to discuss when it comes to this. It's a pretty simple, straightforward thing, but the mechanics of it require a lot of practice. You have to remember all the definitions and all of the identities from trig. So not just the stuff that we've been doing this week, but also all of this inverse trig stuff. And then you have to be comfy with all the integrals we've been doing this week. You have to be comfy doing all of this stuff, calculating all the trig integrals. So while it's an easy and fast lecture, it's not an easy and fast homework. It's a fairly tough homework. And then the other thing we're going to cover next week is partial fractions. Partial fractions is a little bit complicated conceptually. I'll do my best to convince you why it works, and of course I promise you it does work. But there's no convenient, easy way to write the whole rule down in a single line. So you're going to have to remember some different cases and different setups. Could I see just use a react, give a thumbs up react if your pre-calculus class discussed partial fraction decomposition. Holy shit. All right, so we're coming in from scratch there. That's okay, it's not the end of the world. For some reason, pre-calculus teachers are afraid of this stuff. Partial fractions is a way of taking rational functions and splitting them up. Right, so if you have a polynomial upstairs and a polynomial downstairs, you can factor the polynomial downstairs and then ask what sort of functions could I have added up to get that fraction? And it gives us a way of integrating kind of complicated looking things. Those are the two topics we're going to cover next week. After we finish covering section 7.4 on partial fractions, we will be ready for the test. So, reminder, your exam is coming. It's coming soon. I suspect that next Monday we will get through most of trig sub. Next Wednesday we will finish trig sub and get through about half of partial fractions. And next Friday we will finish partial fractions. So next Friday I will send out the study guide. And the study guide is going to be on WebAssign. It'll show up there as like a homework set. You need to solve the problems in WebAssign. But then once you've gone through and solved those, you need to write up nice, neat solutions to every single problem. You will then scan those solutions. I recommend the app Cam Scanner. It works great. Of course, if you have a physical scanner, that's fine. If you have an iPhone, I've been told that the Notes app is capable of doing this. But you need to get your scanned solutions into a single PDF. And then that single PDF you will submit on Canvas. The sooner you submit it, the better, because my goal is to get you some feedback on your written solutions before the test. That way you'll have a clear idea of my expectations. You'll see kind of how I go in and mark things. I'll make comments about how many points I would take off if this was an exam. All of that sort of stuff that you want to know before the test, you can get before the test if you submit the study guide before the test. Study guide will be due on the day of the test, which is most likely going to be, so you said we'd finish 7.4 on the 25th. So the test will be on the 2nd. And I think that puts us a little bit behind in the syllabus, but I want to make sure you have enough time to prepare. So where are we? We wanted to do the exam this week. No, next week. Okay. Yeah, that'll put us about 1 week behind. So over the week between the 25th and the day of the test, this of course won't be all review. That would be insane, but I do want to make sure you have time to work on the study guide. So probably Monday and Wednesday of the week after next, I'll introduce new material. Wednesday we'll review, and then Friday, the 2nd of October will be your first test. Okay, so that's the roadmap. Next Monday, trig sub. Next Wednesday, little trig sub, little partial fractions. Next Friday, partial fractions, and the study guide is released. You want to be working on that study guide over the weekend, and you want to turn it in as soon as you can the week after next. The sooner you turn it in, the sooner I can give you some feedback. That feedback will be valuable on the test. However, the study guide is not due until the day of the test. So if you end up not getting it done or whatever, you're crunched for time, you can hand it in on the day of the test, and the test will be Friday, the 2nd of October. Everybody on board? Alrighty then, I gotta get out of here. I do have my normal office hour this afternoon. So if you wanna solve some more problems, come by there, see me. Otherwise, just make sure you get the homework all done and read section 7.3 in the textbook, okay? Reading through that will help you. If you're nervous about inverse trig stuff, please spend some time in that review material module, and that is it. If I don't see you on office hours, I'll see you next Monday. Take care, guys.